Okay, so now we continue solving this equation and finding the coefficients for this equation. So, so far we talked about these two t and x, and the next step is that we have to combine these two together, okay, to get the final solution of this PDE using separation of variable technique. Okay, so I'm gonna do that. I'm gonna write as u of x and t equals to x times t, right? These two functions. And so based on these, so this is c1 e to the minus k lambda squared t, and this one is x. So let me write it down. First, I'm going to start with x. So x is going to be c2 times sine lambda n x times c1 times e to the minus k lambda squared t. E to the minus k lambda n squared t. Okay, so now I'm going to write this down as c1 times c2, take the constant in one side, sine I'm going to write lambda n x times e to the minus k lambda n squared 2. So now instead of lambda n, I'm going to write np over L here. So I'm going to get un, this is only one solution of n, for x and t, as a function of x and t, is going to be, instead of c1 times c2, I'm going to write d, and I'm going to write it as dn, because this coefficient can be different depending on the lambda n. And instead of lambda n, I'm going to just write n pi over L of x times e to the minus k n pi over L square t. Okay, so this is one solution of ux, and the general solution is if you sum all the different n's here, okay, because n can be, as here we had, right, from there we can say that n can be 1, 2, 3, etc. So the general solution of this PDE is u of x and t equals to the sum of all the possible solutions, or all the n's. So I'm going to say sigma of n equals to 1 to infinity of dn sine n pi x over L times e to the minus k n square p square over L square t, or time. Okay, so this is going to be the general solution of this ODE, and I'm gonna Keep it because this is an important result. So the only thing that remains here, that remains unknown here, is what? The only unknown is dn, right? Which is a coefficient. We know n is going to be 1, 2, 3, etc. The only unknown is dn. And we have to specify what is dn. Okay, so the next step is to find dn from what? Initial condition, right? We have used the boundary condition to find these C2 and C3. And now, in order to find dn here, we have not used initial condition yet, so we have to use initial condition. And the initial condition of the problem was given as this: ux at time equals to 0 equals to fx. So I'm going to write this down. So ux and 0 is going to be fx. So this is the initial condition that I have. And so this is going to give me ux at 0 from here. I'm going to get is going to be sigma n equals to 1 to infinity of dn sine n pi x over L, and then the second term is e to the power 0, which is going to be 1. Okay, so this equals to fx. Okay, so this is going to give me this initial condition is going to give me this information that fx or these dn's equal to this. So this is going to give me a relation between dn and fx, right? So I know that if I multiply sine n pi x over L to dn's and then sum all of them, I'm going to get fx, okay? But we still don't know what is dn. So we have to find what is dn to be able to close this problem and find all the unknowns in this solution. So the trick that we are going to use is from Sturm-Liouville problem, and we will use the fact that the eigenfunctions of the Sturm-Liouville problem form an orthogonal set. So here, these are the solutions for Sturm-Liouville problem, right? So these are actually the eigenfunctions, right? So this one was eigenvalue, these lambdas are eigenvalue, and this is eigenfunctions, right? So I'm going to use this fact that they all set an orthogonal set. So this means that, so that is the inner product of un and um should be 0 for all n not equal to m. So if n is not equal to m, the inner product of them should be 0. So I'm going to use this fact to be able to find all the dn's here, the dn coefficients here, okay? So hence, or let's say thus, multiply both sides of that equation by, so this is a trick that I'm going to use, so I'm going to multiply both sides by sine m pi x over L and integrate over the domain. Okay, so this is actually the definition of this orthogonality or orthogonal set or L2 norm in the Hilbert space that we discussed last time. Okay, so I'm gonna do this for this equation for both sides. I'm gonna multiply it by sine m pi x over L and take an integral over the domain. So integral of 0 to L of fx times sine m pi x over L dx equals to sigma n equals to 1 infinity of the integral of 0 to L dn sine m sorry, this one is n, if you see here. So sine n pi x over L times, then I multiply this by this sine. So I'm going to multiply it by sine m instead of, now m instead of n, m pi x L times dx. So now I come up with this equation, and what I want to do is I want to open this sum, all the terms of this sum, and use the fact that un and um, the inner product of them, is orthogonal for n not equal to m. Okay, so let's get started. So the first term is going to be 0 and L d1 sine n equals to 1, right? So it's going to be pi x over L sine times sine m pi x over L dx plus the second term, integral of 0 and L n equals to 2, so d2 sine 2 pi x over L times sine m pi x over L dx. And this goes on and on until n equals to m. So then I have the integral of 0 to L. When n equals to m, we are going to get dm sine, first term is m pi x over L, second term is sine m pi x over L dx, and then this goes up to infinity, right? Because n can be infinity. Okay, so now I'm going to use this fact. If un and um are not, n and m are not equal, then this integral should be what? 0, right? Because this is u1 and um. So this should be, this is the definition of that, so this should be 0. The same thing for this one. So all the terms are going to cancel out and become 0, and the only term that remains is this term. Right? So this is the only term that remains. So let me show it. Okay, so this is the only remaining term in this summation. So I am left with this. So this tells me that the sum of n from 1 to infinity of integral of 0 to L dn, I'm writing the right hand side, sine n pi x over L times sine m pi x over L of dx equals to only one term, which is this term written here, the blue with the blue line over that, integral of 0 to L dm sine square m pi x over L dx. Okay, so this is an important result here. And if you take this integral, and dm is a constant, so it's going to be dm integral from 0 to L of sine square m pi x over L dx. So if you use some trigonometrics relations, you will get this is going to be L over 2. So you are going to get dl over 2. So calculate the integral using Euler formulas or some trigonometric relations, and then you will come up with L over 2, and this is going to be your final solution for this sum. Okay, so here we are left with this. So this tells us that the integral dm times L over 2, and this is dm. So let me write it again. So this is going to be dm times L over 2. So dm L over 2 equals to the left-hand side here. So it's going to be the integral of 0 to L fx sine m pi x over L dx, right? And so this is gonna give me the dm relation that I wanted. So this is actually the dm was the unknown. I wanted to find this to close the equation. So this is gonna give me the dm is 2 over L, the integral of 0 to L fx sine m pi x over L times dx. So this is also important. Relation that we found. And now the final solution is gonna be, so the final solution of this PDE is gonna be ux and t equals to, I have it here, right? So I have everything now. I have dn, I have this one, and for n and m, I just I can just substitute instead of the m, right, dn, right? So just change the name of m and n, and I'm gonna get the relation that I want. So here I have sigma n from 1 to infinity of 2 over L, so this is dm, integral of 0 to L fx sine, instead of m now I have to write n because this is going to be the n in the equation, n pi x over L dx times, so this is going to be dn, I have dn now, I wrote dn, and then the second one is going to be sine, and then we had this term, right? So I'm just going to write them down, times sine n pi x over L times e to the minus k square n square pi square over L square t. And I don't have, sorry, this one is not k square. So let me just I don't know why it's not working. So this one is not correct. So this is k n square p square pi square over L square times t. And so let me also, what? Okay. Mark this down because this is also very important. The final solution of our ODE, the PDE, sorry. So the 1D transient heat equation, right? So it's going to be partial u over partial t equals to k partial u over partial x square for x between 0 and L, and the initial and the boundary condition that was given in the problem. So with those initial and boundary condition, this is going to be the solution of this equation, and the initial condition was given as ux and 0 is fx, and the boundary condition was given at u at 0 and t equals to 0 and u at L and Z and T equals to 0, right? So these were the boundary conditions. So this is the solution to this PDE that we found using the separation of variable techniques and Sturm-Liouville theory. And as you see, for fx, this can be a general function of x, which is the initial condition. For example, you can just set it to 0, and then the whole thing here is going to be 0, right? So there is no heat transfer with this equation if your initial condition is also 0, because the boundary conditions are already 0. So the only way this is not going to be 0 is your fx has a value. For example, fx can be just 1, or like it can be any function of x, right? And then you can solve this equation and the solution. And so yeah, so this was one example of separation of variable technique for solving PDEs. And I just want to make a general note here. So a general form for dn. So this is the general form. If you want to find dn, you can just use this formula for your problems. So you take the inner product of f, the initial condition fx, and unx, and then divide this by the inner product of un x and unx, so itself, the function with itself, okay? And the inner product is, if you remember, it is just the integral of those two functions times the weight function of that, okay? So you can just check this formula here to make sure that it is correct, but this will be the general formula for finding dn, okay? So you take the inner product of these two to get the dn coefficient in any separation of variable problem. And then the second point that I want to make is about this equation, rewriting this solution, but I wanna make a point here that what do these actually mean, and make a connection with the next part of the course that we are gonna talk about. So this solution is composed of one time component, which is k lambda n t, right? So this is one part of our formula, lambda n square, or lambda n, depends on here. So I'm gonna write it lambda n, and then we have the second part is gonna be square root of 2 over L sine, this is going to be lambda n square because I have sine lambda nx here, so it's going to be sine lambda n x, and then the next term is the integral from 0 to L of fx prime. This is a general form, but I want to write it this way to make a point about transformations, lambda n x prime dx prime, which is the integral inversion formulas, integral transformations, which is the part of the next topic. So this, I just rewrote this right here. I just rewrote this one here, and this function is just a normalized eigenfunction, right? So this is just a normalized eigenfunction, and this is an integral transform. And what we come back about transformations of equations, PDEs, which is very important technique in solving PDEs, even in numerical techniques. When you want to solve a PDE, you usually take it to Fourier space or Fourier. You do the Fourier transform, which is kind of one of the integral transforms, and then solve that, because that is gonna make your computations much faster, and also it's gonna convert the simplify the derivation in your PDE system. So this is the integral transform that is shown here, and then the whole thing here is called inversion formula. So we are going to show that we can get the same solution here by doing integral transformations, or like complex Fourier series, these kind of things, and we can get exactly the same solution as here. Okay, so that is for the next topic. And for the next time, I'm going to solve one quick example of these separation of variable technique, and then after that we are going to go to the integral transforms, which is the next part of the course. Okay, so just go and brief overview of and review of this lecture. We started with the separation of variables, which is a technique to solve PDEs. We have to propose a solution in this way to be able to solve these kind of problems, and then we solved an example for a 1D transient heat equation with this form for this PDE, and we solved it by using this separation of variable technique. So we proposed this solution, and then we substitute that back into this equation that we have, and we get this equation here. And then what we did is we separated the variables into two parts, so all the t's in one part and then all the x's on the other part, and we showed that the only way these two functions, f of time and g of x, can be equal is that if they both equal to a constant, and this is we called minus lambda square. And then based on that, we got two equations, one for time, which we solved that, and we found this is going to be the solution of it. And then one for x, which we found this is a Sturm-Liouville problem, and based on the discussions we had last time, we found the solution of this. So this is going to be the eigenfunctions and also the eigenvalues. And after that, we compose and we form the general solution of this PDE, which is this one. And in order to find, the only unknown was here the dn, the coefficient here. And in order to find that, we use the fact that the E functions of the SL problem set an orthogonal set. So form an orthogonal set, or the inner product of un and um is going to be 0 for n not equal to m. And based on this, we open the summation, and we found a formula for dm, which is shown here, and also the initial condition based on these two. And then we wrote the final solution of this problem, which is shown here for this problem. And this is the final solution of this. And we made some remarks for dn and also the inversion formula integral transforms that we are gonna see in the next lectures. Okay, thank you very much, everyone.